Inverse Z transformation by using method of convolution. So first, convolution theorem of Z transformation. Convolution of two functions f of t and g of t is a new function created by the combination of f of t and g of t that shows the amount of overlap of one function g of t as it is shifted over another function f of t. So how the two functions are overlapping each other, that is what convolution. So just you take a graph, sine wave, and you take another wave, right, cos wave or something, overlapping one and sine wave and cos wave. So that is the combination, right, of the sine wave and the cos wave. That is convolution. It will show how shifted over the another function. One function sine wave is how shifted over the cos wave. That is what the convolution, right? It is denoted by f of t star g of t or f star g. F of t and g of t are discrete sequence. Then the convolution of f of t and g of t is defined by f of t star g of t, which is equal to, if it is a discrete case, you have to take the summation. If it is a continuous case, you have to take the integration. K is equal to 0 to t f of k g of t minus k. Or f star g is equal to, you can extend to the other part, minus infinite to plus infinite f of t into g of t minus k. If f of t and g of t are continuous, then the convolution of f and g is given by f star g is equal to integral 0 to t f of k g of t minus k dt, or f star g is equal to integral, you can change the limit, minus infinite to plus infinite f of k g of t minus k dt, right? F of f star g, convolution of f and g is equal to convolution of g and g star f. Convolution theorem of Z transformation statement. If f of z and g of z are two Z transformation of f of n and g of n respectively, then z of f of n convolution g of n, which is equal to f of z into g of z, where f star g is the convolution of f of n and g of n. Also, z inverse of f of z and g of z, which is equal to f star g. Proof. We know from the definition of Z transformation, f of z, which is equal to z of f of n, is equal to summation n is equal to 0 to infinite f of n z power minus n, and g of z, which is equal to z of g of n, which is equal to summation n is equal to 0 to infinite g of n z power minus n. Now f of z and g of z, multiplying these two, you will get summation n is equal to 0 to infinite f of n z power minus n into summation n is equal to 0 to infinite g of n z power minus n. Now expanding, so f of 0 plus f of 1 z power minus 1 plus f of 2 z power minus 2 plus etc. etc. nth term f of n z power minus n plus etc. etc. Similarly into g of 0, g of 1 into z power minus 1 plus g of 2 into z power minus 2 plus etc. etc. nth term g of n z power minus n plus etc. etc. So multiplying each and every terms, f of 0 into g of 0. It next z power minus 1 term, right? F of 0 in the first bracket and g of 1 in the second bracket. F of 0 into g of 1 z power minus 1. Similarly, second term in the first bracket, f of 1 into z power minus 1, and first term in the second bracket, g of 0. So f of 1 into g of 0 is z power minus 1. So z power minus 1 is common. So second term f of 0 into g of 1 plus g of 0 into f of 1 into z power minus 1. Similarly, you take z power minus 2 terms. In the first term, first bracket, f of 0, first term. The second bracket, third term, right, g of 2, whose coefficient is z power minus 2. So f of 0 into g of 2. So first term, right, z power minus 2. Then similarly, you take the first term in the second bracket, g of 0, and third term in the first bracket, f of 2, g of 0 into f of 2 into z power minus 2. That is also z power minus 2 term. Next, you take the second term in the first bracket, f of 1 into z power minus 1. Then second term in the second bracket, right, g of 1 into z power minus 1. f of 1 into g of 1, z power minus 1 into z power minus 1. Adding powers z power minus 2. That is also z power minus 2. So taking z power minus 2 outside, you will get f of 0 g of 2 plus g of 0 f of 2 plus f of 1 into g of 1 z power minus 2 plus etc. etc. We are going to the z power minus n coefficients, right? So similarly, f of 0, then g of n plus g of 0 f of n. Then here first term, there g of n minus 1 term, right? That power is z power minus n, right? Z power minus n plus 1 minus 1 get cancelled, you will get z power minus n. So plus etc. etc. Then z power minus n, that plus etc. Therefore, f of g in g of g, which is equal to summation n is equal to 0 to infinite. I am taking the nth term. So whenever you are grouping a series, right, in the summation, you take the nth term and put the summation notation. That's all. So here the nth term is f of 0 g of n plus f of 1 g of n minus 1 plus etc. etc. g of 0 f of n into z power minus n. So put the summation notation, which is equal to summation n is equal to 0 to infinite. Suppose if you are having, for example, 1 plus 2 plus 3 plus etc. etc. plus n plus etc. etc. So whenever you are writing in the summation notation, summation n is equal to 0 to infinite, nth term n, right? Suppose 1 square plus 2 square plus 3 square plus etc. etc. n square plus etc. etc. Writing in the summation notation, summation n is equal to 0 to infinite n square. So whatever it is, we are taking the nth term and the summation notation. Here the nth term is, that means z power minus n term into summation notation, right? So you will get f of g into g of t, g of f of z into g of z, which is equal to summation n is equal to 0 to infinite f of 0 g of n plus etc. etc. g of 0 f of n z power minus n. That is z of. So when you are applying the z transformation definition, so z of f of n, which is equal to summation n is equal to 0 to infinite, right? First condition. Then the function f of n, whatever it is, f of n, then into z power minus n. So here you are having the summation n is equal to 0 to infinite. Then the function into z power minus n. The function is nothing but f of 0 g of n plus f of 1 g of n minus 1 plus etc. etc. plus g of 0 f of n. So that is nothing but z of f of 0 g of n plus f of 1 g of n minus 1 plus etc. etc. plus g of 0 f of n. Right? Therefore, this is equal to summation z of summation k is equal to 0 to n f of k g of n minus k. So here you can write the z of f of 0 g of n plus etc. etc. plus g of 0 f of n can be written as, because this is also a series summation, right, with summation. So it can be written as summation k is equal to 0 to n f of k g of n minus k, right? See, when you are putting 0, so here what is the general term, that is nth term. Instead of nth term, we are taking the kth term, whatever it is. So in order to write in summation, so for that kth term, what is the kth term? F of k, right? First is f of 0, second f of 1, right, plus etc. etc. Then f of 2, f of 3, like that. You take like that, and then multiply by g of n minus 1, right? Similarly, the kth term is f of k, into g of n minus 2. See, for the first term f of 0, g of n minus 0. Then f of 1, g of n minus 1. Then next term f of 2, g of n minus 2, right? F of 3, g of n minus 3. So kth term is f of k, g of n minus 3. So we can write it in z of summation k is equal to 0 to n f of k, g of n minus 3. So f of g into g of g, which is equal to z of, this is nothing but the convolution. That is for the discrete series, f star g, right? From the definition of convolution. Therefore, f star g is equal to, so taking z inverse on both sides, z inverse of f of g into g of, f of z into g of z, right? Now z inverse of f of z into g of z, which is equal to f star g, is equal to z inverse of f of z convolution z inverse of g of z, right? Convolution of two functions. So it can be written as z inverse of f of z. F of n is nothing but z inverse of f of z. And convolution g of n can be written as z inverse of g of z. So z inverse of f of z into g of z can be written as z inverse of f of z convolution